earlier video, we have seen the introduction to Jablonski diagram. What exactly is the Jablonski diagram and what are the depictions or energy transitions which we can depict in the Jablonski diagram. Now, today in this video, I shall elaborate more on the various aspects which we find in the Jablonski diagram. Particularly, we shall be focusing on the non-radiative transitions and radiative transitions. Now, first let us see what are the non-radiative transitions. Now, to understand the non-radiative transitions, let us go on to the energy levels of the system. Now, we have the ground state energy level S1, the first excited state energy level, S2 the second excited energy level, and so on. And as I had said earlier, we do have the vibrational levels within each electronic states, within each electronic energy levels, and they are depicted as V1, V2, V3, V4, etc. Now, here on the screen you have only the singlet level, so singlet electronic states, wherein the electrons are having opposite spins. Now, when the electron or the molecule or the species absorbs energy from the light radiation, it can go to higher excited states, higher energy levels or higher electronic states. And here the electron has moved from the ground state to the second excited state, to the vibrational levels of the second excited state. Now, we know that any system prefer to come back to the ground state. There are various ways by which the system can reach the ground state from the excited state. Now, here the molecule or the system is in the vibrational level of the second excited state. Now, from there it can come down to the various vibrational levels of the first excited state, that is from vibrational levels of S2 to vibrational level of S1. Now, this is called internal conversion or depicted as IC. Now, internal conversion happens between S2 and S1. It does not happen between S1 and S0. Now, the reason is because the energy difference between S2 and S3 or between S1 and S2 is less than the energy gap between S0 and S1. The energy difference of energy between S0 and S1 is very high. Okay? So, the internal conversion is not possible there. Internal conversion is possible only when the electron or the species gains energy and goes to the second excited state and above, and then it comes back to just adjacent lower electronic state. Now, this internal conversion again does not involve any radiation or emission of radiation, and the energy dissipation is happening by transfer of energy from the excited molecule to other molecules around it via collision. Okay? So, this is a non-radiative transition. Now, here when you see the after internal conversion, the electron is in a higher vibrational level of the excited electronic state. Now, from there this electron can come down to the lowest vibrational level of the excited state. Okay? So, here the green arrow mark or the green transition is showing the transition of the electron from higher vibrational level of one excited state to the lowest vibrational level of the same excited state, and that is vibrational relaxation. So, the difference between internal conversion and vibrational relaxation is that internal conversion happens between two different excited states, while vibrational relaxation happens within the same electronic state. Now, vibration relaxation can also occur when the electron is excited to the first higher vibration level of the first excited state, and from there it comes down to the lowest vibrational level of the same excited state. All right. Now, this also can happen. The third possibility is that the electron accepts energy from the ground state, it goes to the higher vibrational level of the same ground state, does not go to the higher electronic state, but it remains within the ground state, but at a higher vibrational level or at a higher vibrational energy level. Then also what happens, the electron can come down to the lowest vibrational level of the ground state. There also vibrational relaxation happens, and that is also a non-radiative transition. Now, this relaxations, that is the internal conversion and vibrational relaxations, both are very fast transitions. Okay? They happen immediately after the absorbance of light. As soon as the light is absorbed, it goes to excited state and comes back quickly down to the ground state. Now, if we just compare the internal conversion and vibrational relaxation, there is not much difference in the time span taken for these two. Both of them happens within the range of 10 to the power of minus 14 to 10 to the power of minus 11 seconds. The major difference between the two is that internal conversion happens from higher electronic state to lower electronic state, while vibrational relaxation happens from higher vibrational state of one electronic state to the lowest vibrational state of the same electronic state. Another point when we look at the internal conversion and vibrational relaxation is that these two are not the final relaxation mode or final transition mode. If it is internal conversion, it can undergo vibrational relaxation. From there, it can undergo radiative transition. And if it is vibrational relaxation, again from there it can undergo radiative transition or our intersystem crossing, that is another non-radiative transition. Now, we will see how intersystem crossing is happening. So, we have all these radiations, the internal conversion and the vibrational relaxation. So, our electron which has been excited and which has been relaxed has reached the lowest vibrational level of the first excited state. From there, if the energy level of the excited state, singlet excited state, is overlapping with the energy level of the triplet excited state, then it is possible that the electron can transit from S1 to any of the vibrational levels of T1 which are overlapping with each other. Now, when this happens, there will be spin flipping, the spin of the electron will be flipped or the spin of the electron will change. Now, until now when we were talking about internal conversion and vibrational relaxation, the spin of the electron has not changed. The electrons are in the same it is in the singlet state. The multiplicity is 0, spin multiplicity is 0, it is in the singlet state, sorry, spin multiplicity is 1, it is in the singlet state. But when intersystem crossing happens, the spin changes and it moves on to triplet state. Now, this is quantum mechanically forbidden process because of the spin flipping, but then it happens because we include the vibrational relaxation and rotational energy modes there. Now, once the electron reaches the triplet state, higher energy, higher vibrational level of the triplet excited state, from there again it can undergo what is called internal conversion, vibrational relaxation from the higher vibrational level of the triplet state to the lowest vibrational level of the triplet state. Now, from this one, this involves change in multiplicity and it is a slow process. Since there is a spin flipping, it will be a slow process and it takes 10 to the power of 8 to 10 to the power of 3 seconds. So, it is slower than the internal conversion and vibrational relaxation. All right. Now, coming to the radiative transitions, we shall move on to the fluorescence first. Now, the Jablonski diagram for fluorescence we can explain using, explain in this way. We have the electrons which goes from lowest ground state to the higher excited state. From there it undergoes internal conversion or vibrational relaxation. Now, from after vibrational relaxation, what can happen is, from the lowest vibrational level of the first excited state, the electron can come down to the lowest or the other vibrational level of the ground state. And when this happens, if there is emission of radiation, then we say that it is fluorescing. And that emission of radiation, the radiation must fall within the UV visible range, that is 200 to the wavelength must fall between 200 to 800 nanometer. So, remember when we talk about radiative transition, the radiation which is being emitted must fall within the UV visible range. So, fluorescence can happen when the electron move from the lowest vibrational level of first excited state to the ground state, maybe higher vibrational level of ground state or the lowest vibrational level of ground state. Now, this fluorescence is again a slow process when compared to internal conversion and vibrational relaxation. Remember, it is a radiative transition, it loses energy much more in the form of radiation, and the process is in the order of 10 to the power of -9 to 10 to the power of 7 seconds, and it happens between the first excited state and the ground state. That is important. Fluorescence happens between first excited state and ground state, singlet excited state and singlet ground state. So, the spin multiplicity of the electron is not changed when the molecule undergoes fluorescence or when the molecule shows fluorescence. And fluorescence is an allowed transition as the electron's multiplicity is not changed. Now, one more aspect here is that the energy of the fluorescing radiation will be less than the energy of the incident radiation. Now, we know that because the when the incident radiation is absorbed, some amount of energy is transferred or converted for or used up for internal conversion, vibrational relaxation, etc. And only the rest is being emitted as fluorescing radiation. So, the energy of the fluorescing radiation will be less than the energy of the incident radiation. All right. So, we can show the fluorescence as absorption happens, then internal conversion happens, then vibrational relaxation happens, then fluorescence happens, or absorption, then vibrational relaxation, and then finally fluorescence. These are the two pathways by which we can explain fluorescence. Now, in the case of atoms which does not have vibrational energy levels, the emitting radiation, the wavelength of the emitting radiation will be equal to the wavelength of the exciting radiation or the incident radiation, because there are no vibrational energy levels in atoms. So, in the case of atoms, we call it as resonance fluorescence, all right, because in atoms there will only electronic states, but not vibrational states. Vibrational states or energy states are found in molecules. So, in the case of atoms, we call the fluorescing atoms, they undergo resonance fluorescence. And fluorescence emission stops as soon as you stop the source of excitation or as soon as you stop the source of light. Fluorescence stops. In the case of phosphorescence, it is not so. We shall see how or why it is so. All right. So, these are the points related to fluorescence. Now, examples of compounds which are fluorescing in nature, you have the solution of quinine sulfate, which emits bright blue fluorescent light. Then you have alcoholic solution of chlorophyll, which fluoresces with deep red color. This you can try out in your lab. You take a leaf, crush it, extract the chlorophyll, the green, and then you expose it to light, you can see deep red color. Another example, fluorite, riboflavin in petroleum, they also fluoresce, and vapors of acetone, sodium and mercury. Vapors of sodium and mercury will be showing the resonance fluorescence, because they are atomic in nature. the rest are compounds. So, they will be showing fluorescence, that phenomena is called fluorescence. Now, coming to the phosphorescence, fluorescence involves electron transitions within the same singlet electronic state. But for phosphorescence, triplet state also comes into picture. Now, we have excitation of electron, it goes to higher energy level, it undergoes relaxation by internal conversion, and then it undergoes vibrational relaxation. All right, different various modes of vibrational relaxations are there. From there, it undergoes the non-radiative intersystem crossing, which we had discussed earlier. Now, after intersystem crossing, it will undergo vibrational relaxation, again a non-radiative transition. From here, that is from the lowest vibrational level of the triplet excited state, the electron will come down to the ground state of singlet state. Remember, we are transferring, or the energy transition or the electronic transition is happening from the lowest vibrational level of triplet state to the lowest vibrational level of the singlet state. So, here what is happening? There will be again spin flipping, the spin of the electron will be changed. Now, when this happens with the emission of radiation, that is within the UV visible light, then we call it as phosphorescence. Now, this is a very slow process, and this involves spin flipping twice. One spin flipping happens when the intersystem crossing occurs, and the other one happens when phosphorescence happens, that is when the electron moves from a triplet state, lowest vibrational level of triplet state, to the lowest vibrational level of singlet state. It can also happen when the electron moves from lowest vibrational level of triplet state to other vibrational level of singlet state. The only thing is there must be emission of electromagnetic radiation which falls within the UV visible region. Now, phosphorescence is a slow process. It is a quantum mechanically forbidden process because of the spin flipping happening, and the lifetime when the molecule or the electron remains in T1 is longer, and it remains in the triplet excited state for a longer time before it goes down to the ground state, because it has to change its spin. The electron has to change its spin. Hence, the emission of phosphorescence is slow and delayed and persists even after the light is removed, source of excitation is removed. That is why, that is how, we have this glow in the dark toys, we have clock dials which glow in the dark. That is because they are made up of, they contain chemicals which are phosphorescing in nature. So, even if you remove the light, it will glow in the dark. So, they are phosphorescing material. Now, regarding phosphorescence, it happens between the triplet state and the singlet state. And the phosphorescing energy will be definitely lesser than the incident energy, as we have explained for fluorescence, the same reason, because various other transitions comes in between before phosphorescence happens. And hence, it is a slow process. There will be change in spin multiplicity, and the luminescence is delayed by 10 to the power of more than 10 to the power of -7 seconds after excitation. You excite it and it is delayed by 10 to the power of -7 seconds, and then only phosphorescence happens. And it takes 10 to the power of -4 to 10 to the power of -1 second. And it continues even after removal of the source of excitation. Now, examples like glow in the dark toys, stickers, paints, clock dials, etc. contain phosphorescing material. Now, we can depict phosphorescence as absorbance, internal conversion, vibrational relaxation, intersystem crossing, again vibrational relaxation, and then phosphorescence. And examples of compounds which show or which are phosphorescing are inorganic phosphors like oxides and nitrites, silicates or oxyhalides doped with small amount of activator ions. like rare earth and transition metal ions. Alkali and alkaline earth metal sulfides containing trace of heavy metal sulfides also show phosphorescence. Now, examples: zinc sulfide, calcium sulfide, strontium aluminate, and certain complex organic compounds. These organic compounds are used in OLEDs, that is organic light emitting diodes also. So, this is about phosphorescence and fluorescence. The Jablonski diagram of how we can explain phosphorescence and fluorescence using Jablonski diagram, the various energy transitions. Thank you.